Hello, everyone. I'm James Chuang from Synopsys, and today my presentation is about the journey to the best performance per watt at 3 nanometers and below. So this is the agenda of my presentation today. I'll go through some of the new emerging implementation and sign-off challenges you may see at 3 nanometers and below. And in the second part, I'll talk about how the Fusion design platform of Synopsys, with its unique platform advantage, could solve some of the challenges there. And also in the third part, most importantly, the sign-off backbone that Synopsys has, the golden sign-off solution suite, how that could address some of the emerging challenges that you will see at 3 nanometers and below, and how that could also help your implementation flow produce much better PPA. All right, so getting into the challenges at 3 nanometer and below, I think the first one is not about the implementation itself. It is about the broad design space that is now available to you at these advanced nodes. Compared to other established nodes, there's a lot of options that are available to you at 3 nanometers and below. Starting from the power delivery, the power delivery network, there's a lot of options, different grid sizes, pitches. The voltage levels are even broader than before. We saw that increase when we went from planar FETs to FinFETs, but now at 3 nanometer and below, you have a very, very broad range of voltage, of operating voltage for you to choose for your specific chip. Variation models also evolved over the years. In established nodes, we were on OCV. About 5-10 years back, we started AOCV. Now POCV and LVF-based POCV are all available to you as variation modeling techniques, and how to choose from them for the best balance between performance, between margining, and your final yield is also a vector that will be available to you, and you have to make the decision. On top of that, the library choices, now with the transistors, there's 1 fin, 2 fin, 3 fin. There's a lot of variations of the library cells. Therefore, we expect that the PPA exploration compared to established nodes would be much, much broader. And there will be a lot more trials that you will be doing to make sure that you're getting the most out of the new technology nodes, and that is going to be best for your design. So that's going to be the first challenge, the challenge of a vast variety of selections that you have when you go to this advanced node at 3 nanometers and below. And on top of that, what's new in 3 nanometers and below, an emerging design trend is that previously in some nodes, you will have different versions, different flavors of a node, right? There's, for example, at 5 or 7 nanometer, there will be a compact version of that node that is better for area. And there will be a high performance version of that node that would be best for speed. But at 3 nanometer and below, we have seen major foundries introducing variable row heights. You could have them mixed, meaning that it wouldn't be a consistent row. It doesn't have to be a consistent row height throughout your design. It could be a mixed row height throughout your design if you so choose. And the mixed row height does bring its benefits. For example, if you look at the red chart over the red curve over here, this is for the shorter cells, the compact, the area advantage cells. You would see that the speed of those cells would not be reaching a very, very high performance. However, it will bring area benefits if you so choose to run at a lower speed. On the other hand, if you choose for the tall cells, even if you run at a lower speed, the area would be still at a disadvantage versus the short cells, but the tall cells would reach a much higher speed. If you had mixed rows, then it's the best of both worlds, right? You would be able to use mostly the shorter cells if you're running at a lower speed, and you would still be able to reach a much higher performance if your design needs that. Using these mixed cells, you have a lot more opportunities. So the goal is that using these mixed tall and short cells, you could achieve the better performance per watt. So basically, you achieve a smaller area while improving the performance at the same time. So giving you that flexibility to trade off between a better trade-off between area and performance. But this also brings more complexity, more options, more selections, choices you have to make when you do your designs at 3 nanometer and below. Okay, the I wouldn't say the last one, but also a very important emerging trend we see at 3 nanometers and below is the high resistance layers. This is not new. The high resistant layers were always there at 7 nanometer. Typically, it would be the lowest 4 layers. At 5 nanometer and 3 nanometer, as the EUV layers and as the EUV layers become more broadly available, we see the smaller pitches also for more layers at these nodes. So there are area benefits, but also because of these smaller pitches, the resistance goes up, right? So if you look at the trend over here, this is just an illustration. You would see that the capacitance of the wires doesn't go up very fast, but you see the resistance. The unit resistance of the wires and the vias go up tremendously when you go from 7 nanometer, 5 nanometer down to 3. So this higher resistance means that the interconnect delay, the interconnect timing, can no longer be just an estimation during your implementation. It will play a much bigger role in your overall timing, in your overall critical timing paths as you go into 3 nanometer and below. So your implementation throughout the flow from implementation to sign off, you need a consistent methodology, an accurate methodology to make sure you capture the interconnect timing and the overall impact to your design throughout the entire flow. Okay. So next, I'm going to talk about the Fusion Design Platform. Synopsys is the Fusion Design Platform and its unified platform and advantage. And how does that address some of the critical challenges I talked about in my previous section? So first of all, most importantly is that physical synthesis is now essential for variable row designs. Variable row designs, as you see here, once you decide the amount of short row heights versus the tall row heights, during synthesis, when you select the cells, you need to be able to manage the site row densities for the tall and short cells. For example, if the synthesis flow does not consider the balance between the tall and short cells, the synthesis tool might choose all the tall cells because it's best for timing. Or it may also choose a lot more short cells because it's better for area without considering the local density of the tall and short cells for a certain part of your chip. So that would cause a lot of issues. That would cause a lot of issues. You can't have one area of your chip that is dense on short cells, where the other area of your chip that is dense on the tall cells. That will cause all sorts of routability, all sorts of placement issues. So with Synopsys Fusion Compiler, with the physical synthesis, it's building the logic netlist and the physical placement at the same time. So in addition to considering just the area number or the performance number, the timing numbers, it's actually placing the cells into those rows and managing and balancing the site row density and the cell usage of these tall and short cells on all of the areas in your design. So this would provide the best, of course, the best performance, power, and area metrics, but also ensure that the congestion, the convergence is going to be managed throughout the flow and make sure the convergence is going to be proper as you go through the place and route stages in your later phase. So just as an example, we had a Asia mobile semiconductor company. These are the first ones that would go into these variable row heights because they have high performance and low power requirements at the same time. They use variable rows, and what they have is this mobile HPC core, very high performance core that at the same time also needs to be small in area and low in power. This project had very aggressive schedules, and we were with using the physical synthesis capability. Not only did the tool meet a much higher frequency than the previous target and much smaller area, but the engagement was also short, indicating that there was not a lot of back and forth. That if a designer was using a pure logical, non-physical synthesis capability, they might get stuck in some of the backend where, like I was saying, if they overloaded the short rows, or they overloaded the tall rows in certain local areas. So this 7-week engagement and very, very successful engagement indicates that the physical synthesis is really delivering a very convergent and very predictable flow for 3 nanometer variable row height designs. Okay, now we talked about interconnection. In the past, at established nodes, the cells were much slower. The cell timing, cell delays were much larger than the interconnect itself. So a lot of the optimization, a lot of the considerations were around the cells. Should I use big cells, small cells, tall cells, short cells? What is the variation modeling for those cells? Interconnect is often just a simple calculation, and it's not given that much of a consideration during optimization steps. But as I was talking about the interconnect layers, the increase in resistance for those min width layers, now interconnect could be up to could be dominating your critical timing paths. 50% of your critical timing paths might be dominated by wire interconnect delays. So now we have a bit much bigger focus on optimizing the interconnection during the overall design optimization. And as you go into 3 nanometer and below, it's a compound effect too. Not only the interconnect is slowing down because of the higher resistance, or having a bigger delay because of the higher resistance. The cells are also much faster, right? So the 3 nanometer and below, those cells switch much faster. Therefore, the ratio tips even stronger to the interconnection side. So having a full flow capability to optimize for routes is going to be critical for convergence and for exploring the best PPA for your design. And with the Fusion design platform, with Fusion Compiler, because it has everything from synthesis, placement, clock to route, all in the same platform, the routing engines are available very early everywhere in the flow. So even during the later half of synthesis, even early during the clock tree, the routing engine is available right there. So you would be able to have a full flow routability optimization that could enable for a higher design utilization. You're not trying to cover up, you're not trying to recover during only at the late routing stage, but you're considering all those routability issues, those interconnection timing issues that could possibly happen, and addressing those very early on in the flow at a structural level. And with that, we are able to improve the routing congestion that is potentially going to happen downstream. And with that, you are able to pack more cells, pack more or increase the utilization of your chip early on in the flow without causing routability issues downstream. So typically utilization optimization or boosting, you trying to utilize more area in your design is something you do in the front end, and just fingers crossed that it wouldn't cause issues in the back end. But now with the Fusion design platform, we are able to pack higher utilization early in the flow, while still ensuring that the routability will not become an issue as you go through the later half of the flow. Another consideration on the physical side is test integration, right? One of the things that always comes in from the left field or as a curveball is the test insertion. Many times you had completed your synthesis flow, everything is physical compliant, but the test logic comes in and it will break a lot of things. And one of the challenges in the past that people were getting by with established nodes and all that is that a lot of times test insertion is done without the physical information. Yeah, the test flow is done on a purely logical netlist. The scan chains, the scan insertions, all of those things are done on a logical space without truly considering the physical impacts of those newly introduced logic. Now, with the integration of Synopsys TestMax and Synopsys Fusion Compiler on the Fusion Design platform, these two tools have common engines. They're sharing the common database, and there's the TestMax test insertion is going to be physical friendly, and the implementation of the new test logic is fully physically aware, and it's very targeted for the type of new logic that the test would bring in. So on the right-hand side, you could see a few examples. For example, the left column here is all these test steps that are done without physical information. And this has been a traditional flow for 20 years plus. And you could see that this is typically what people see, right? When the test logic gets adds, it comes back. A lot of the hotspots, routability issues, the routes just go everywhere. But with physical awareness in test insertion and true physical optimization being done with Fusion Compiler, when these two are done hand in hand, you could see that it's not that hard. The scan chains, test insertion, those are not complicated logic. You just need to be physically aware so that the ordering, the congestion, the test point connections, and the pipelining is all done in the physical space, nice and neat. So you see that just with the physical domain, with the physical information, your test insertion could look much cleaner and converge much faster. And it improves PPA, because when you end up with a design that has routes all over the place like this, you will spend a lot of area adding buffers to fix those scenic routes. You use up a lot of routing resources that should be later available for other optimization, and that's taken away. So that also impacts PPA. So with a fully physical aware test insertion and integrated test and implementation engine, these improvements could be easily seen as a differentiation, and that is critical for 3 nanometer and below, because the physical optimization is already very challenging, and you're addressing one of the most physically challenging circuits that was previously there in the flow. All right, now we talked about very early on. I talked about all the new options, the increased number of options that's available to you in 3 nanometer and below technology nodes. So we have an AI, because human trying error, and just trying all sorts of things are not very productive. That's not very productive. Human don't read data, big data, very efficiently, but AI does. So we have the world's first autonomous AI app called DSO.ai. What it does is that it could explore trillions of design recipes very efficiently and very effectively, looking at multiple objectives at the same time. And it's fully integrated with the Fusion Design platform. So of all the options, we looked at all those 5 different vectors, all the combinations. DSO.ai would be able to find a much better result based on what the human intention is. And in this case, for 3 nanometer and below, we used it to optimize the amount of short cells versus tall cells, short rows versus tall rows in the floor plan. That's an option. You could choose to have 2 more short rows versus the tall rows, or 2 more tall rows versus the short rows. There's always this variable ratio as well. What is going to be best for your design? It takes a lot of trial and error. So what DSO.ai did is that it took the 2 baselines that the human came up with, and just went and explored what the other optimization techniques, what are all the other vectors are coming in, and what is going to be the best combination. You could see that it could push the power and timing profiles to a much better direction versus what human could do. Overall, you could get in this case, they got a 18% better timing result and 7% lower power. So with the vast increase in options and selections, AI is one of the techniques that are quickly being introduced to address this. All right, my last section is going to talk about the sign-off challenges and the new techniques that are coming in to address them, and also how that integrates into the Fusion Design platform as the backbone. First and most importantly, the entire sign-off backbone is fully integrated at the code level within Fusion Compiler. Synopsys has all the sign-off, golden sign-off tools in the industry, and all of those engines are not being called. They are at the code base being integrated with Fusion Compiler. So there's no 2 timers, 3 timers, different timers. For using prime time as an example, when Fusion Compiler wants to do a timing calculation, the engine that comes up and calculates that is prime time. If Fusion Compiler needs to figure out what the RCs of a new net is, the calculator that comes up, the extractor that comes up is the star RC extractor. So all of these things are fully integrated. All the sign-off engines are fully integrated into Fusion Compiler, so that when Fusion Compiler is doing the optimization, the reference is always the sign-off reference. And I'll show you a few examples why that is going to be critical for 3 nanometer and below. First of all is interconnection. We're back to interconnection again. We talked about interconnection, the timing of interconnection being much more important, because now it's dominating 50% or more of your critical paths. Now, throughout history, we have been working on OCV, AOCV, POCV. All of those variation techniques are all targeted for cells. Interconnection was usually just a global margin. Now that interconnect timing is so important and so dominating, a global margin means that you're leaving a lot on the table. So with this in mind, we wanted to improve the variation modeling in interconnection. So we have worked with various major foundries to enable the wire variation, the interconnect variation, new syntax in your variation modeling that could describe the variation profile of the interconnection as well. So no longer you are using a flat global margin for all of your interconnection timing. There will be a global component that will still be more or less like what a global margin would look like. There's also going to be a local component that is going to be considered. There is going to be statistical cancellation. All of those variation pessimism reduction techniques could all kick in for your interconnection variation. And for that, your timing is going to be much more accurate and not over margining. So, this variation, interconnection variation, is going to be enabled at a lot of 3 nanometer and below technology nodes to make sure that this dominating timing component is not over margined and is very accurately modeled. Very importantly, this is fully enabled in Fusion Compiler. So when Fusion Compiler is doing the optimization, it also accounts for the interconnection variation, just like you are doing it in the sign-off phase. All right. Last but not least, we have the voltage aspect, right? We talked about the FinFET having a much broader operating voltage range, 3 nanometer and below, even broader. So a lot of customers, a lot of our designers are exploring how to run at a lower voltage, because that has tremendous benefits to the dynamic power, especially for HPC, especially for mobile applications. So it's not as straightforward. Previously, we usually look at the timing critical path, and these timing critical paths have the strongest drivers, have all the strong cells, which is less sensitive to voltage change. So when you're trying to run at a lower voltage, those are not the paths that you have to take care of. It's actually the secondaries, right? The paths that were not that critical. So you traded it off for smaller area, for higher VT. Those are much more sensitive to voltage. So, those would be violating much sooner as you start dropping the operating voltage. And in those cases, we need to be optimizing those paths, the voltage sensitive paths, so that your design could be running at a further lower voltage. And that is not just the optimization piece, it's also the analysis and robustness as well. You at 3 nanometer and below, smaller wires could also significantly increase the resistivity on your PG network, which means that IR drop would be potentially much more pervasive in your three nanometer in and below designs. So making sure that your design is not sensitive to IR drop, and how and not just relying on the dynamic IR drop analysis, but making your design robustness robust and robust against any IR drop that could happen. You could find out, where the sensitivities are, where are the high sensitive cells, the cells that are highly sensitive to IR drop, and making sure that those are not on the timing critical paths. So these are the type of analysis that are going to safeguard yourself from potential chip failures downstream that is going to be caused by IR drop. So, we also have this voltage and timing sign off, meaning that not just looking at the IR drop, but also looking at the timing impact this IR drop could cause. Because, if an IR drop happens, it causes some timing shift, but it's not on a critical timing path. That's not going to be a big issue. But we need to take specific considerations for the cells that are sensitive to IR drop, which means that, a slight change in the voltage would cause a much bigger timing shift. And we need to make sure that those cells don't exist in critical timing paths to cause a problem. So that type of analysis is also new and also becoming much more popular in 3 nanometer and below. Again, these type of analysis not just available in sign-off, but also available in the implementation flow, so that when you're doing the optimization, this is already accounted for, and making sure that, hey, the design is going to be robust against variation, is going to be robust against voltage changes as well. All right, so we have Fusion Compiler as the implementation tool. Many times when you go into sign off, you don't want to bring back the whole Fusion Compiler implementation again. So we have Prime Closure, our new ECO solution that shares the physical engines of Fusion Compiler and takes all the sign off information very efficiently into account, multi-scenario capabilities that could handle hundreds of scenarios at the same time, which is only visible at the sign-off stage, and then close the design based on that sign-off information. This physical engine also supports the variable row height properly. It shares the same engines that Fusion Compiler has, and you can see here on a 3 nanometer case, 1 million instance block. Before ECO, sign-off was reporting about 20,000 violations with about more than 200 nanoseconds of TNS. This is because the vast amount of scenarios that pop up during the sign-off phase, we are seeing extremely high fix rates and 100% 3 nanometer rule compliant. So, having a physical, not just physical aware, but physically very capable the timing and power closure engine at the end of the flow that fully supports all the 3 nanometer and below physical rules and these legalization requirements is going to be critical for your 3 nanometer and below designs. All right, in summary, Synopsys has the Fusion Design Platform, which has the implementation and the golden sign-off engines, and should be your most trusted partner for 3 nanometer and below designs. Our expertise in not just EDA, but also in the IP and library space and AI is going to provide vast benefits when you're doing the process exploration or evaluation for 3 nanometer and below. And we talked about Fusion Compiler being the industry's only RTL to GDS2 solution, being able to consider the physical concepts, the physical constraints very early on in the flow. And that could enable the best variable row height, the design PPA optimization. And of course, the Synopsys sign-off solution continues to deliver the best accuracy to drive your design PPA to the most accurate level that is possible. And also having that serve as the backbone of the Fusion Design Platform is going to be critical for a proper 3 nanometer and below design implementation and sign-off. So that concludes my presentation. Thank you very much for your time today. And everyone, you have a great day.